Yep. Because 5 is...
So more than likely, if everybody there finishes 5 turns in on Friday, you have solutions coming up.
Right, and I might post solutions before you guys turn them in, and that's okay. Like, you guys can, like, if I end up posting solutions beforehand, you can check your work against my solution. It's not, like, it's fine. It's, you know, the point is learning. I'm less concerned about judging which one of you is best, you know. We'll work that out with, like, some arm wrestling at the end of the semester. So or something like that, I don't know. Maybe, okay, so let me try to give you a introduction to surfaces in R3. And so we're not just talking about, you know, what is a surface in R3. We're trying to describe surfaces in R3 in such a way that the way we're describing it naturally leads to a deeper discussion of what are called manifolds. All right? And so I think it's kind of fun to just talk a little bit about the history of manifold. So the term manifold comes from Riemann. Riemann was Bernhard Riemann was one of the students of Gauss. Gauss was influential in him having a career and such. And anyway, when Riemann became a professor, he had to give this big talk. Or maybe not when he was a professor, but when he became a better professor, like, I forget what it was. It was a big deal. He had to give this big talk about, like, his big idea. And he gave a talk about basically the concept of extended n-dimensional space. And so in this talk, he described what he meant by a manifold. And he was German, so he didn't say manifold. He said Mannigfaltigkeit. I'm saying that wrong, but something like this. It looks kind of like manifold if you look at it. Mannigfaltigkeit. I'm reading from the Wikipedia article on the history of manifolds and varieties, if you're wondering. But so when Clifford, of Clifford algebras, anyway, that's another story. When he read some of Riemann's writings, he translated it into English as manifoldness, right? And I mean, the word manifold has been around in English since, that's not a new term to the 19th century, right? If you happen to ever read there's like, if you read the King James Bible, which is from, like, I don't know, when's the King, well, from whenever King James was, right? But this is old. And like, I know there's a verse in King James, like manifold, talks about the manifold wisdom of God, right? It's like something like many folds, right? Many directions, the idea of the word. So the word manifold in English certainly predates this talk by Riemann, which was like mid-19th century. But it's interesting. See, so certainly in English context, this word that Riemann used for extended n-dimensional space typically translates into English as manifold. But in other languages, like French, right, and other quote-unquote romantic languages, it tends to get translated as variety. So in mathematics, there's two sort of very, well, they're not entirely separated or anything, but some people study varieties, some people study manifolds, all right? And so varieties are more like solution sets to equations or systems of equations, right? Whereas a manifold is more in tune with what we think of as like a parameterized surface in Calculus 3. You've seen both in Calculus 3. We sometimes talk about a surface as the level set of an equation, right? That would be like the variety viewpoint. Whereas we sometimes talk about a surface as, you know, you give me x, y, and z as functions of u and v, where u and v are parameters, right? That's more the parametric viewpoint or the manifold viewpoint. And the funny thing is, the term manifold and the term variety actually, as they're used in modern mathematics, typically probably can be traced back to this one talk that Riemann gave in the mid-19th century. It's just that the word got translated in two different directions, depending on which language you went into, which I think is hilarious. But Riemann has said, among other things, like one of the things Riemann said in this speech is that his concept of an n-dimensional space, you could think about it as being composed of a continuous stack of n minus one dimensional spaces. Right? Does that make sense? Think about a two-dimensional space, it's like a collection, a continuous collection of one-dimensional spaces, right?
That's how I think of like three-dimensional space. It's like if you have one sheet of paper, that's a 2D surface, you stack
Just like stacks of sheets of paper, yeah. And even that, and that's not a particularly, in some sense, that goes back to Euclid, right? If we remember the discussion we had at the start about his axioms and concepts, there's a concept of a surface and continuing lines, and like, there's already some kind of idea of at least of a two-dimensional surface. Anyway, surfaces in R3. So this is really what we're describing, I would say, from a more abstract perspective, is what we would later call a two-dimensional manifold, right? And so here it is. So first of all, we have to define the ingredients. And so one of those, I'll use a big X for it. Big X is going to be mapping from D, subset of R2, to R3. And this has to be open. What does it mean to be an open subset of R2? So what I'm defining right now is a quote-unquote proper coordinate patch, okay? So the properties that we insist on for this X are X has to be 1-to-1, X has to be smooth, X has to be regular, and X inverse, which is going to be a mapping from X of D back to D, has to be continuous. Now, that term, regular, all right, regular here means that the Jacobian of X, let's say Jx, has rank 2 throughout D. Okay, so yeah, let's give an example. So we could have X of uv equal to, let's say, uv u squared plus v squared, all right? And what do you want to make the D? Well, D is at a subset of R2. Well, I'll say D is equal to R2, just to be lazy. All right? D is equal to R2. That's an open set. A set is open if any point in the set has an open disk around that point. It's got no like solid edges. It's only got fuzzy edges. Have I not talked about this at all?
Are you talking about the surface? Doesn't have like...
Well, R2 is a plane. I said it's open inside the plane.
So it's a fuzzy edge.
Well, if I take for example the closed disk, this is not open in the plane. because if I take this point on the edge, I cannot find an open disk around that point, which is inside the set. So points on the edge are not interior points. Did I talk about interior point and boundary point in here?
I remember this talk like I want to say maybe the day.
Okay. My memory's fuzzy. I can't remember if we ever had the talk about topology in here or not.
So the circle is a set, and a point in that set can be defined with more than what's only in that set.
What I'm saying is, like, generically speaking, if the set I'm looking at has all like fuzzy edges, even if there's like a hole in it, it's still going to be an open set, because if you pick any point inside the set, any point, I can find a little open disk around that point. So every point's interior. Aha! Hooray! If I could just remember what I did 3 weeks ago. Yeah, closed means the complement is open.
What does that mean, like to have a circle around it?
What does what mean?
You pick a point and you can build a circle around it. What is that?
That means that this is an interior point.
Well, how do you know you can not have a circle around it?
Well, I mean, it depends on the set, but this one, this closed disk, the edge point, I can't help but have points outside that are not inside D, right? There does not exist a disk of any radius which fits inside D and surrounds that point. So this point here is not an interior point. In fact, that's an example of what's called a boundary point of D, right? The boundary of D is, in fact, the unit circle in this case. Uh-huh.
I really don't remember. I see it in my notes.
That did exactly this example. I am a creature of habit, but if you take like the Cartesian product of open intervals, it's open. For example, if I took 1, 2 Cartesian product with, say, 3, 4, that would give me like a rectangle that goes from 1 to 2 and from 3 to 4, and it gives me like this little that's an open set, because you pick any point in there, you can find a little open disk around that point, which is inside the set. Every point's interior.
What is the low? Sorry.
It
That's
dep-
what I'm not understanding. Like,
What?
is the low? Like, what do we?
Well, you have to be able to, to prove it, you have to be able to give an argument for an arbitrary point that you can select some delta, so that delta disk around that point is a subset of the set which we're looking at. In this case, the square with the dotted edge.
Okay, so it's essentially
We call this thing S.
you have to have, it's only open if every point in the space is a subset of the big.
It's only open if every point in the space is an interior point.
Which, and if it's an interior point, it has to be a subset of the space.
If it's an interior point, there has to exist an open ball around the point, which is within the set.
Okay, that makes sense.
So, in summary, open sets in the plane, they're sets that are they have fuzzy edges if they have an edge.
No,
They can be infinite,
yeah,
but
I get it.
okay. So now that we're done with that tour down memory lane, let me go. Hey, wait a minute. Am I supposed to put topology on the test? That's okay. I did talk. I did talk for about an hour about inner product versus metric space versus normed space versus, Banach space. Like, I don't see that being in a question on the test because that was for like your information. We haven't really had homework problems on that, right? So I think the homework should be very informative about what's most important. So anyway, getting back, is this one-to-one?
Yeah, for every input you have an output.
So you could prove one-to-one directly, right? If you set x of uv equal to x of u bar v bar, let's say, that would give you uv u squared plus v squared equal to u bar v bar u bar squared plus v bar squared. And from that, as you guys have already told me, this is equal to that. This is equal to that, which shows us that uv equal to u bar v bar, right? So we can prove it's one-to-one easily. It's one-to-one. Is it smooth? As a general rule of thumb, if you have formulas, it's smooth. We have formulas. Now that can you can come up with a formula which fails to be smooth. It's not that hard to do it, but if the formula makes sense, it's probably smooth. These are smooth. Is it regular? What does that mean? I said Jacobian has rank 2. So the Jacobian here would be partial x, partial u, partial x, partial v. So I'm using u and v for the parameters of the patch. And so that's, what is it here? Well, that's 1, 0, 2u, 0, 1, 2v, right? And so those vectors are linearly independent. So in fact, this is right. These are linearly independent, no matter what u and v are. Therefore, rank 2. Consequently, this map is regular. Now, did you say something about cross product a minute ago? That would be a good test, right? If the partial velocities of the patch were linearly dependent, that would mean that they're collinear, which would mean then that their cross product was what? Zero, right? Because if they're collinear, cross product of vectors of the same direction, 0. So like an equivalent, you want to test, we could test this. Partial x, partial u, cross partial x, partial v is not equal to 0 for all u, v, and d, right? If you had that, that's a convenient and simple criteria to check regularity of the map. We can just check the cross product of the partial velocities. That's an equivalent way to characterize regularity. Now you guys know Calc 3. What am I saying? I'm saying that a regular surface has a well-defined normal vector field, right? Because that's what this is. Partial x, partial u, cross partial x, partial v, that is the normal vector field to the surface. We'll come back to that eventually. It's going to be a while. We'll spend a long time talking about normal vector fields in here, hours. Okay, so continuous, sure. I guess that would beg the question, what is the formula for the inverse map? Can you tell me?
Way back in pre-cal, it was like y with x.
Yeah, I guess if I want to really make good on that threat, I need to do some algebra here. So I'm going to say x of uv equal to, for lack of imagination, so I guess I should just say xyz, right? So I need to solve x equals to u, y equals to v, and z equal to u squared plus v squared for x, y, and so let's see here. I want to say, what is x inverse of x, y, z, right? It's supposed to be uv, right? So for this one, it's very dumb. What can I do? What can I put there? I can just put x, y. Yeah. Now, this is for x, y, z, but you gotta, so the thing that makes this a little bit, notice that x inverse is a mapping from where? X of d to d again, right? So we have x inverse of x, y, z equal to x, y, right? That's for all x, y, z in x of d. Now, what is x of d, though? That's x, y, z such that what? It's not just any old x, y, z, right? It's a specific subset of x, y, z, subject to a very particular condition. Z is u squared plus v squared. Z is x squared plus y squared. So the sneakiness of the inverse map, it's all kind of tied up in the domain of it. Like, it doesn't look like it has anything to do with z on first glance, but it does because the x and y are taken together with z, which is tied to x and y in the sense that z is equal to x squared plus y squared. So this thing that we just derived is called a coordinate chart. The coordinate chart is the inverse to the patch. I think O'Neill at some point says they're interchangeable. I disagree with this a lot. Patch goes from the parameter domain up to the manifold. Chart goes from the manifold back down to the space of parameters, the Rn. They're inverse concepts, but I think you can see why the introductory books focus more on patches, because patches are easy to understand, right? Patches we do in Calc 3. Chart, that's a kind of weird new idea. But in any event here, I can draw a picture for you, right? So what we're looking at is what? This is M. M is equal to x of d. This is a surface. So the, I mean, it goes on and on. You know, that's just a picture of it. But this is nothing more than a paraboloid, right? This is a paraboloid. Paraboloid is an example simple surface. Why is it a simple surface? A simple surface is one for which you can cover the whole surface with one proper coordinate patch. All right?
You can cover the whole surface with one coordinate patch.
Right. This is one coordinate patch, it covered everything.
Oh, so you're saying like if you need two equations?
If you need more than one coordinate chart to cover more than one patch, maybe it's not a simple surface. I mean, if it took two, that doesn't prove it's not a simple surface, right? To prove it's a simple surface, to prove it's not a simple surface, you would have to prove somehow that there does not exist a patch for that set of points, which covers it all at once. that seems a lot harder, right? Now, so you're like, you haven't really defined what a surface is yet, have you? I'm like, nope, I did not do that yet. Let me get to it. Hey, did I never define it? Son of a gun. Well, looking at my handwritten notes, I don't think I ever actually came out and wrote it down, but here it is. A surface M, a subset of R3, let's say, is a set with a collection of patches which are compatible. And that's also known as an atlas. So let me draw you a picture. So I mean, this is just heuristic picture, all right, but maybe for some reason the details of this surface allow you to cover this piece of it, all right, with one patch. All right, so this is one patch. So D maps up here like that via the patch X. All right. Then the other part of the surface over here you can cover with another patch. All right. We'll call it D bar, and for lack of imagination, I will call that X bar. I also use Y, a big Y, whatever, that's another. So I'm supposing both X and X bar are regular coordinate patches, one-to-one, you know, non-vanishing vector, non-vanishing normal. In other words, the rank 2 condition, and the inverse is continuous and they're smooth, right? Then compatible. What does compatible mean? That means if I look at the function down here, I can go from one to the other in the natural fashion. Compatible means that, let's see here. How can I? So it's going to hit the intersection. All right.
Compatible if you can write an equation from one to the other, so they're all at points in their set?
It means that they don't disagree with each other where they overlap, in a sense. In the sense I mean that. What I mean is that they don't give incompatible in the sense of smoothness descriptions of the surface where they both say something about the surface. It doesn't mean that they have to map to the same point or anything like that.
Like, okay, I see what you're saying. It's one
So-
can say something about that particular area that the other one doesn't.
Yeah, well, I'll give a specific example here in a minute, but you guys just have to help me out here. So if we take a point, let's give this intersection of these two things, let's give this a name. Let's call it U equals to the intersection of x of d and x bar of d bar. All right, so I'm just going to call that U for the sake of having a name for it. And so back down in here, there's x inverse of U. That's this. That's some subset of D is x inverse of U. All right, and that's going to map over here to something over here, which would be x bar inverse of U. So this little blue will get mapped over to that little blue. Like basically, just to tell you the story of the point, if this is the point right here, right? This point right here, let me call it P, maps up up here to x of P, and then that back down here to where it goes to. So that would be x bar inverse of x of P, right? So you can follow a point back again. In other words, the natural map to look at down here is x bar inverse composed with x. Compatibility of the charts, all right? Excuse me, compatibility of the patches means that the composite of the inverse with the patch of the other is smooth. That's what compatible means. And you also need this one. These both have to be smooth. No, I don't think we're ever actually going to check that for any of our examples. I'm just saying, like, technically that's what's needed. All right. Maybe I think I may actually work it out for an example, but we need an example, right? We need an example where we have more than one coordinate patch needed, right? What's that? Oh, good. And in fact, this definition I'm giving, it's the same as the definition for manifold. A manifold is like an abstract set with an atlas, and when you compose the charts, they have to be compatible in a very similar sense. So when we, in a week or two, just talk about what a manifold is, just a little bit, this will naturally generalize there. That we are. I'm just saying when I actually have examples, I'll at least give you a token example or two of a whatever dimensional manifold, you know. Okay, so example 2. We could do this. We could have x of uv equal to uv square root of 1 minus u squared minus v squared. And we could have, say, x bar, u bar v bar equal to, I don't know, u bar square root of 1 minus u bar squared minus v bar squared v bar. All right. And this would be for d equal to uv such that u squared plus v squared less than 1. And this would be for d bar equal to d. Same set, different letters. But it's the same point set. Those are open sets. Now here's a picture of what's going on. All right, so let's try to understand this. We've got x equals to u, y equals to v, z equals to the square root of 1 minus u squared minus v squared. What is this? We've got what? Z squared equals to what? 1 minus x squared minus y squared, right? What is this? Hey, check it out. This is nothing more than a parameterization of the unit sphere, in part. What part? Not the whole sphere, right? This parameterizes what? Z greater than what? Greater than 0, right? Does it equal 0? I don't think it does, because to get 0, we need u squared plus v squared equal to 1, which we do not have. Right?
No, you don't think a negative one can't square.
Right, I mean, exactly. So, but I don't actually, I have defined D to not allow that, right? So we could picture this. This is what? Right, it's the upper hemisphere, right? Right? How about x bar? We've got what? X equal to u bar, y equal to the square root of 1 minus u bar squared minus v bar squared, right? Z equal to v bar. What's this give us? Again, x squared plus y squared plus z squared equal to what? Equal to 1, right? Same algebra. But now this is for y greater than 0. So in our usual picture, it's like this. Right? So that's a patch on the, I mean, depending on how you want to, the language you want to endorse. If this is the east, I don't know, whatever you want to call that, the right half of the sphere, right? My picture's kind of hard to, the Z, I don't know, don't make me draw the x-axis on my picture. It doesn't go well. Here I can draw it. Now, these do not form an atlas on the sphere, right? The sphere as a point set includes the up, the down, the left, and the right, right? So, but if I'm so foolish as to try to draw both at once, right? There's a place where these intersect, right? It's, yeah, the first quad, I guess, quadrant, I don't know, what was it, octant maybe? Yeah, I don't know. Up in here, right? And we could try to write the formula for the transition. Those are called transition functions, by the way. These are the so-called transition functions from one coordinate map to the other, one patch to the other. And we could try to write the formulas for the transition functions for these, right? But in order to do that, I'd have to find the formula for the chart not just the patch, right? I mean, we could do that. I think this example is sufficiently simple. We probably could work it out. Yeah, it's very stupid, right? Like, what's x inverse? I'll write it up here in yellow. So x inverse of xyz is what? xy. How about x bar? Yep. Yep, xz. Cool. So whenever we use some of the existing Cartesian variables as parameters, the inverse maps are pretty easy to write down. What gets trickier is like when you look at a parameterization where you're not using the Cartesian variables for any of your formulas, something where you have a more interesting parameterization, right? Then the inversion process could be impossible by hand or something. I mean, you know, you might have existence theorems showing you that it exists, but in practice it might be just untenable to find formulas. That can happen. We have that situation all the time in calculus, right? We sometimes talk about you can integrate this function, or you can't integrate this function, right? But the fundamental theorem of calculus says that if you have a closed interval and you have a continuous function on that closed interval, the antiderivative exists, right? But that doesn't mean that you can find a formula for it. All right, finding a formula for the antiderivative and its existing as a function, those are two separate goals, which we often confuse. But anyway, okay, so can we look at the transition function here? Which one do you guys want to look at? X bar inverse composed with x, or what?
Go to the top hemisphere to the right hemisphere. So x into x bar.
So x inverse composed with x bar? All right, so we're going to feed that uv. So we get x inverse of x bar of uv. What's x bar of uv? Yeah, but x bar of uv, we defined it over there. It's u bar. Oh, yeah, but the thing is, I would agree with you, but I guess I should, to be fair, I should put u bars here, just to stick with my current notation. Sorry about that. So u bar squared minus v bar squared. Oh, thank you, v bar. Oh, no square in the last one. And then what's x inverse? We just keep whatever's in x, and we keep whatever's in y. Right? And then I said it has to be smooth. What do I mean by that? I mean it's smooth in the sense of advanced calculus. As a mapping from R2 to R2, it's a smooth map. Pragmatically speaking, the way to judge that is if you can calculate the Jacobian matrix, and that Jacobian matrix has, if you can take partial derivatives of the component functions of the map to arbitrary order, and they're all continuous, then it's a smooth map. So the question is context here. Can we take partial derivatives of these? Like if I call this thing f, what's the Jacobian of f here? Right? What's that look like? 1 minus 2 u bar over 2 square root of 1 minus u bar squared minus v bar squared, right? 0. And I learned my lesson. I'm not going to write the 2 down next time. You know, they cancel. I mean, all I've looked at so far is the first derivative. But it's usually enough to look at that and you can kind of tell. If you keep differentiating, if you take derivatives with respect to u bar, v bar, these things, it's going to still be things of this type, right? So what's the condition we need in order for this function to not blow up on us? It's okay provided what? So long as 1 minus u bar squared minus v bar squared is not equal to 0, right? But it's not, because what do we assume? We assume that u bar v bar is in D, well, or D bar, which anyway is specifically designed to avoid that. So these are compatible. Now, to get an atlas on the sphere, what do we need? We need more charts, right? We could do what? The easiest thing to do, you need to, you got this? Okay, come over with me. I'm about to increase our number of charts by 2. Behold, what we already have is the plus. That's the northern hemisphere chart. Southern hemisphere chart, x minus. This is the right half. Here's the left half. Those 4 charts cover all the points on the sphere. Right? You got the upper half, you got the lower half, you got the right half. Do we miss? Oh, we're still missing 2 points, aren't we? You have to see if I can draw a picture of it. Right, we're missing this point. Let me tell you their coordinates. We're missing the point on the back, which would be like x equal to, oh good grief, what is it? It's -1, 0, 0, I think. And the point on the front, 1, 0, 0, right? We're missing those 2 points. Yeah, I mean, I've got the whole right half. I'm missing this point and this point in particular, right? So on this, I get up here, you know, I pick up. From this one, I pick up all of these. But I never got my paws on the ones on the equator. And, you know, when I throw in the southern, I get all of those. But I'm always missing those 2 pesky points on the equator. So this is not an atlas for the sphere yet. These 4 patches together don't form an atlas because they don't cover the whole sphere. For an atlas to be an atlas, we have to cover the whole sphere. So I need 2 more charts, right? And I'll put them up here. I'll call them y. I mean, why not, right? Y plus minus uv. And how about you guys tell me the formula for them? I'll do the hard part. Plus or minus square root of 1 minus u squared minus v squared. Something like that. Now, we might find out later that we need to reverse the order of u and v because of the issue of orientation, but we'll come back to that when we get to it, okay? These might actually not be consistently oriented charts. There's something else to worry about. The orientation of the charts is compatible. That means that the determinant of the transition functions has to be positive. If the determinant of the transition function is negative, that means that the normal's flipping from one side of the surface to the other as you go from one patch to the other. I'd actually have to do some thinking about that. It's not hard to think about. It's 3 dimensions. So you just have to think about partial x, partial u, partial x, partial v cross product. Where's that point? And you need to check that they line up. For example, we need to check that they're all outward pointing. They may or may not be that. I mean, I might have, if I had to worry about that, there's something else to think it through. But setting aside the issue of orientation, this is an atlas. These 6 charts, rather 6 patches together, forms an atlas for the sphere. And the sphere, by the way, is an example of a surface which is not simple in the sense that we defined earlier. You cannot find a single patch that covers the whole sphere. Now, you might be like, but I thought we did in Calculus 3. Didn't we parameterize the sphere in Calculus 3? How did we parameterize the sphere in Calculus 3? Do you guys remember? Spherical coordinates, I like that. So what are spherical coordinates? Usual math spherical coordinates. Rho, cosine theta, sine phi. It's better? It's better. Y equals to rho sine theta. Sorry, I'm referencing I was harangued earlier for my improper and ambiguous notation concerning theta and phi. Anyway, there you go. Very different looking. Anyway, yes. So a sphere is just rho equals to 1 unit sphere, right? So we could do x of phi theta equals to cosine theta sine phi, right? Sine theta sine phi cosine phi, right? And this is, of course, for 0 less than or equal to phi less than or equal to pi, 0 less than or equal to theta less than or equal to 2 pi. So one thing, we're already into trouble because what's our domain for this parameterization? Yeah, our domain is actually 0 to pi, Cartesian product with 0 to 2 pi. That's a closed set. So you're like, well, I'll just make it bigger and open, right? Just make it go bigger and give it fuzzy edges. Then what do you run into trouble? Like, what if I just tried to just make it a little bigger, Go like, I don't know. So here's a picture of it in phi theta space. Right? There's a picture of the domain for our usual spherical parameterization of the sphere, It's closed, right? If you try to make it just a little bit bigger to make it open, I mean, you could do that. You could play that game, right? Just go a little bigger. Make it open, right? What happens then? What's the trouble? It's still you can feed any value of phi and theta you want into these formulas, but the point is that there's that degeneracy, that 2 pi periodicity of sine and cosine, which come back to get you, right? Like if I go beyond pi here, I will cycle back. I should say circle back. That's what we say now, circle back. I will circle back to the value I already have. It won't be 1-to-1. Like that choice of 0 to pi and 0 to 2 pi, it covers all of the sphere at least once. In fact, it's already not 1 to 1 though. Because if you think about the sphere, right? Well, the 0 to pi is okay, right? 0 sort of is naturally identified up here, right? And the minus z in some sense is naturally identified by phi equal to pi, right? But the trouble is with theta, right? Theta's in there. And this is theta equals to 0. This, you know, how can I say this? The xz plane, right? Xz plane is where theta equals to 0. But what else is on the xz plane? How about where's theta equals to 2 pi? That same plane, right? 0 and 2 pi are the same geometric location in terms of polar coordinates. And so you're like, oh, well, we just need to weaken our definition of chart. You're being too, what's the word? Cantankerous. And demanding it be open, right? Suppose we weaken it a little bit. Just do this. There we go. Now we don't have the 0 to pi problem anymore, right? Sure, fair enough. We don't have the 0 to 2 pi problem anymore. And I think phi's okay. So then does that work? Does it have all the other properties that we want of a regular coordinate patch that I've erased now? Is it 1 to 1? Is it smooth? Does it have an inverse that's continuous? It has equations, so yes. I don't know. Let's work it out. This one's going to sting a little. We have x equals to cosine theta sine phi, right? We have y is equal to sine theta sine phi. We have z equals to cosine phi. Can you solve that for theta and phi? That's what we have to do, right? We want x inverse of, well, rather phi theta. So well, I guess z is easy enough, isn't it? All right, fine. So we got that much. I'll put in, there, we've accomplished at least one component. Hooray. But how do you, wait a minute. I'm an idiot. No, I'm a dummy. This is why I should stop lecturing after like a certain point. I think we're to that point. X, Y, Z. I want this, right? Duh. So what is phi and theta as a function of x, y, and z? That's the question. All right. Cosine inverse of z. All right, great.
Could you say that? Like theta, you can't write in terms of phi.
How about this? Y over x is equal to what? Tangent theta. The phis cancel, don't they? Assuming that what? That